Welcome, everyone. Thank you for joining us for today's webinar. My name is Hebe. I'm the communication specialist at Huawei Transmission and Access Network product line. Today, we are presenting Achieving New Speed with Super 200G, presented by Dr. Maxim Kuschnerovs. Just a little housekeeping before we get started. If you have any questions during this presentation, please type them into the question box in your GoToWebinar control panel. I'll bring them up during presentation, and we'll also have time for questions at the end. Now, without further ado, we'll turn the time over to Maxim. Our presenter today is Dr. Maxim Kuschnerovs, Senior R&D Manager, Huawei Research Center, Germany.
Okay, thanks so much. It's a pleasure hosting this webinar. And our goal today is to talk about Huawei's 200G solution for transport networks, especially for long haul. So the outline, pretty brief. At first, I'd like to show some key industry trends, which the motivation behind our developments and the boundary constraints, which are given to us by our customers, and then lead into a deeper dive on the key technologies which we use in our 200G solution in long-haul transport networks. So looking at the traffic growth evolution over the last 8 to 10 years, traffic growth doesn't stop. It may slow down a little bit. So from the 40% year over year 10 years ago, we're going more towards 30% year over year growth in transport networks, but it's an ever increasing curve. On the other hand, if we look at optical spending for DWDM interfaces, you don't really see a big increase in spend. So all the traffic growth increase must be compensated for with a cost decrease year over year. And for many years, technology obeyed a approximately 30% year over year cost decline. But the last few years, these steps are getting harder to come by, as evidenced by analysts. So what does it mean? What are the reasons behind it? Let me just point out a few examples of why it's getting harder to decrease costs for optical transport equipment. For once, there's the end of Moore's law. I mean, I think it's pretty safe to say it's ending. There's no discussion here. What does it mean? It means that this trend, which we have seen over the last several decades of the number of transistors doubling up in chips within spans of 18 to 24 months, is coming to a halt. The steps to new process nodes, for example, 7 nanometers, 5 nanometers, are further and further apart and becoming also quite expensive compared to previous generations. Meaning it takes more money to invest in new technology, and it takes more time to productize a new technology based on a new node. Furthermore, we're also reaching, or at least saturating, in terms of what a signal processing chip can accomplish in an optical fiber. There's certain physical limits, like the Shannon limit for capacity of a fiber, which we're getting close to. And while there are still improvements in the horizon, we do not see the same big jumps as we've seen in the beginning of coherent optical communication. So this saturation makes each new generation require more and more research and development in order to achieve a similar step as we have seen previously. And moreover, we also at some point will face fundamental changes in architectures. Let's think about electrical interconnects in our line cards, connecting chips and modules. Currently, the industry uses 25 gigabits or 50 gigabit IOs and will surely scale towards 100 gigabit IOs for electrical SerDes interfaces. But beyond 100 gig electrical, we will see a change in paradigm. We will likely have to integrate optical interfaces with Ethernet switching chips in order to be able to transmit over the same distances, be it from chip to module, chip to chip, or via backplane. And that means, of course, a huge change in architecture and a big invest necessary to accomplish such a feat. So all of this means next steps are getting harder to come by. From a network perspective, I think what's been pretty clear in the last few years, we've seen a rise of the cloud and cloud services. And when you look at where and how data centers are built and deployed, there's a clear trend that several data centers are built in areas where the cooling is cheap, because it's really a big hassle to cool a data center, where the real estate is cheap, and we can have access to cheap energy. So, for example, the Nordic countries in Europe, they are favored for these kind of data center deployments. Well, we also see on the left side a similar data center map in China, and in between is a necessity for long-haul interconnects. But the trends in data center connectivity in the last few years have been scaling up pretty aggressively. We have seen a huge adoption of 100 gig. We're now seeing a wave of 200 gig interfaces coming into the market. And hopefully by the end of the year, we will see first 400 gig intra-data center optical interconnects. And this will put a much higher burden on the underlying optical networks which connect these data centers, be it in metro or in long haul. So to sum up, we still continue to see a big pressure on the bandwidth side, fueled by the adoption of an expansion of cloud services and applications, while at the same time, industry-wide is a struggle to continue reducing costs. So the question will be, of course, how do we maintain the innovation? How do we keep pushing it forward? And if you look at the special example of ultra long haul transmission, and the question of how do you go from 100 gig per lambda to 200 gig per lambda, where it's in the beginning was almost a rule that the distance of 200 gig was not as high, not even comparable to 100 gig. Here the question is, how do we make it a seamless upgrade to the customer when we need to upgrade the network from 40 gig or 100 gig going forward? So now, before we go to the more technical part, we would like to have a small poll. So, Hebe, I turn over to you.
Thank you, Maxim. Well, go ahead and take 1 minute for a poll now. And thank you, everybody. I will start the poll for you. Hello, everybody. Please show your point of views now.
So as we see here, the question is, what are the most important aspects of 200 gigabit and transmission networks, also especially in long haul? So here you have the choice. There's multiple answers can also be selected between performance, reach, / DSP innovation, price per bit, low power consumption, and at the same time a high slot density, pluggability, pay as you grow, or / compliance with all greenfield and brownfield line systems.
Let's have a look at the poll results. 65% of the attendees have selected performance and reach and DSP innovation. And the second is low power consumption slot density. And then comes the pluggability and pay-as-you-pro. The last are the price per bit and compliance with all greenfield and brownfield line systems.
There's not just one characteristic, one feature which is most important. There's operators which need to have the best performance and best reach, depending on how they have their network, right? There's operators which need to have pluggability as part of how they design the operations. And I think what it means, if we continue now to talking about the key technologies of Huawei's 200 gig, is that there's not really one size fits it all solution anymore. So when we look at our long haul 200 gig, we offer several flavors. For once, there's the ability to deploy a 200 gig QPSK interface, which offers a 16 terabit per second capacity per fiber at a distance of up to 5,000 kilometers, which is very comparable to existing legacy 100 gig QPSK. So you pretty much double the capacity at the same distance. On the other hand, we have on the other hand, side of the spectrum, we have a format, a 200 gig enhanced 16 QAM, which is able to provide a higher capacity per fiber while still complying to all fixed grid networks. Although in this case, of course, the reach is a bit lower. So we talk about up to 3,000 kilometers. And this is realized, this ultra long haul transmission, also by two dedicated chip developments, which enable us to further lower the power and the footprint and offer specialized solutions. So how does that look like? I think in order to be able to fully judge and appreciate the current generation of any supplier's ASICs or products, it's necessary to look back at the history and see where we all came from. So let's take a look at Huawei's OptiExtreme DSP development timeline for coherent modems, coherent optical modems. It started in 2010 with the first 65 nanometer chipset, which had 100 gig per lambda line rate, was a single line rate, in the reach of up to 2,000 kilometers. That was like the first ASIC, the first 100 gig modem in long haul one could buy. And then you see that every 2 years we have further innovation steps, always using the latest, most advanced process node, so going to 40 nanometers and almost doubling the reach in 2012. Then progressing to 28 nanometers, which further reduces the power consumption of an ASIC and enables us to put in more features. In this chipset, we further increase the reach of 100 gig, while at the same time offered for the first time a 200 gig line side. Then in 2016, we sampled, prototyped an interface, which at the first 400 gig line side single wavelength was based on faster than Nyquist technology using 16 QAM. And while the chip in 2016 was still able to support line card as well as pluggable implementations, for the latest generation, which became available last year in 2018, there was a clear need to have two dedicated chips because otherwise it became impossible to really offer optimal solutions for each application. On one hand, there's the H series, the high performance series, which offers for the first time a 600 gig line rate and a flexibility of choosing a variety of line rates from 100 gig to 600 gig based on 16 nanometers. And at the same time, we sampled the G6, so-called green chip, which had less features by design. The purpose was to really reduce and optimize power consumption and also the packaging size of the chip, and offered a 100 gig / 200 gig line rate for pluggable CFPs. So while the H generation is used in a so-called mini MSA module, which is discretely attached to a line card, the G6 is used in a CFP, which is hot pluggable, and it can be used in across a variety of platforms which support CFPs. Now, I think it's interesting to choose an analogy for how fiber systems are designed. Let's say you compare it to a highway. Now you decide to build your interconnect between point A and B. You roll out a highway with a certain number of lanes, and you design a certain width per lane. So given on the width per lane, a number of lanes, your capacity, which you can transmit in terms of cargo on your truck, is limited by the available physics. And actually, most of brownfield networks are built like this. So there's once you build it and you use so-called fixed ROADMs, fixed grid ROADMs, there is no way to increase the width of a channel. Meaning, if you build a bigger truck, a wider truck, which is able to transport, let's say 200 gig or 400 gig instead of 100 gig, but it just doesn't fit into a single lane, you cannot really send it over this existing highway or this existing system. On the other hand, we also recommend for greenfield scenarios to use flex grid ROADMs, where this width of a lane in a highway can be adaptively adjusted according to the needs of the optical interfaces, which is future-proof design going forward. So if we look at the main modulation schemes and line rates in our next generation modems, the most important are 200 gig, 400 gig, and 600 gig. And the 200 gig, as I already mentioned, we have a clear distinction between a very long reaching modulation format, QPSK, which requires a minimum channel spacing of 75 gigahertz. And we have our own enhanced flavor of 16 QAM, which requires less spectrum and fits into legacy 50 gigahertz networks. Of course, we also have higher rates like 400G or 600G, which can be used to effectively transport multiples of 10 gig, 100 gig clients, or 400 gig clients, depending on what's in the host site. But naturally, for DWDM transport systems, the line rate and the host rate or the service rate are a bit decoupled. There's not one-to-one ratio. So a 600G is not really a service rate. It's just the aggregated rate of several services, which segregation is done by the OTN system. So while this may look promising, saying, well, we have a single interface or a single solution which offers such a variety of different rates, nothing comes for free. And in this case, when we look at the distance versus rate, it becomes evident that, for example, if we go on the top right, if we look at the transmission distance of QPSK, which we norm to 100%, and compare it to a classical 16 QAM, where a 16 QAM modulation would effectively double the throughput per transmission interface, we see that the reach is actually reduced by roughly 75%, which is quite significant. So you cannot just simply double up the modulation and keep the distance, not even close. And going even higher to 32 QAM, 64 QAM, the transmission reach used to be 5,000 kilometers in case of QPSK, reduces to 1 or 2 spans, which is maybe 100 to 200 kilometers in case of 64 QAM. So naturally, while it does give the customer a great deal of flexibility, it doesn't give a seamless update where you can just plug in an interface into an existing system and hope everything else will not change. It does require a change of how you plan, design, and build out the network. So in order to improve the reach of these high order modulation schemes, we of course need to talk about the engine of optical networks or optical interconnects. So similar to the engine in the car, which is the key expertise of each car maker, which defines how fast the car can drive, which defines how much gasoline the car is using per 100 kilometers, or maybe it's even electrical, which defines how much emissions the car is emitting. Same thing for a DSP ASIC. It's at the same time the brain and the heart of the optical interface, and the sophistication inside of this device helps bridging, as seen below, terrestrial networks which can be cross-continental and reach, 10,000 kilometers. In order to achieve this and really bring out the best in each modulation scheme, we have a toolbox of methods which combines really optimize the performance of each given reach and distance. It's called a channel-made shaping. It's a combination of, as we see below on the right, constellation shaping. Constellation shaping is a technique to make the signal look more like noise, so to change the probability distribution of a given modulation scheme, which, according to communication theory, increases the capacity per fiber. The second aspect is Nyquist shaping, which helps us to squeeze in the channel into a given tight channel spacing. So for example, enable a 50 gigahertz channel spacing for a long haul 200 gig. And the third important ingredient is the transmitter precompensation. So it's these are algorithms which not only compensating for impairments of the optical components of a transmitter, but also take into account the complete link, any given link. And thus, the combination of all these techniques into one makes sure that once you plug in an interface into a live network, it adapts to the real scenario at hand and is able to squeeze out the most from any given distance. So if we will look at our track record so far with the 600 gig multi-rate MSA module, we see that we've been quite successful with it. So as evidenced by the industry's first live demo at the NGON conference in 2018 in June last year. We also won the award for the best single channel programmable 400 gig product. This year's OFC conference in San Diego in March, we also been fortunate to receive an award for our 600 gig solution. And of course, it's not just something for a demo in the lab to a customer. We brought it also to the field, as seen below, and demonstrated this prototype in the field in a live network. So on the right, you see how actually this line card looks like using the mini MSA module. It's two MSA modules and one line card discretely connected, giving 2 lambdas per slot. So for example, if the objective is to transmit a 400 gigabit Ethernet client signal over ultra long haul distance, one could use this line card, bundle up these 2 wavelengths, and reach up to 5,000 kilometers with up to 16 terabits per fiber. On the other hand, if we're talking more about a metro scenario or maybe a regional network with up to 1,000 kilometers, we can bundle up and transmit 2 400 gig Ethernet services or equivalent of 8 100 gig Ethernet services with up to 32 terabits per fiber. And of course, the highest capacity case is naturally also the shortest one, more suitable for metro DCI applications where with the 600G per lambda using 64 QAM, one can transmit up to 48 terabits in the C-band. But now, I think what's also pretty clear from this slide is that using 16 QAM as a baseline, the reach is in the range of 1,000 kilometers. So naturally the question comes, what did we improve for our pluggable 200 gig solution to increase the reach and make it suitable for long haul scenarios? So let's talk a bit about the other chip in our latest generation, the low power chip, the green generation 6 chip. It consumes 40% less power than comparable solutions at the same reach for 200G. It combines 3 different ingredients to get to this level. So of course we use an established low power CMOS process of 60 nanometer FinFET. We use low power algorithms for signal processing. For example, innovative dispersion compensation, which enables us to compensate of large amounts of dispersion, which can accumulate in the fiber using tools which actually would normally be suited for very short distances. So a reuse of very efficient algorithms for long haul. Naturally, we also need to invest it in very low power error correction algorithms to reduce the power on the high level. Well, at the same time, as a third ingredient, you need to take all of these algorithms and make a power effective chip design and give actually a power efficient RTL code and optimize the libraries when designing. So all of these 3 combined give us a low power chip which fits into a CFP module while at the same time giving in a long haul 200 gig transmission performance. So how does the actual application look like? I think this is a very nice chart demonstrating this principle. So it's a line card from the OSN 9800 OTN switch. It supports up to 5 modules per slot, giving a total capacity of 1 terabit per slot in an OTN switch. It's as you see here, the main benefit of a CFP is pay as you grow. So if a customer, an operator wants to deploy such a line card, in the beginning, they would only have to buy like the bare metal line card without any line side optics. So you do not need to buy the fully equipped card. And instead, you add capacity when you need and only pay for it when you need it. Same goes for sparing maintenance. If you look at an integrated card, which integrates multiples of wavelengths, like 4 or 10 wavelengths, only one wavelength needs to fail for the whole card to be replaced. And also you would need to spare the complete line card with all the interfaces on if it's discrete. In the case of pluggables, we can spare just one hot pluggable. And if there's a failure, you replace only one hot pluggable, which is a cheaper way of sparing and very easy to maintain. And at the same time, what's even more beneficial, one can use these pluggables across multiple platforms and build networks which are line-side interoperable without any limitations. For example, you could use a core OTN switch, high density, high power switch, which you use in core networks, and make it interoperable with a Metro small form factor chassis, which both would use the same pluggable on the line side. And as you also see here on the right, this module gives the seamless upgradability from existing 100 gig on a 50 gigahertz spacing to 200 gig on a 50 gigahertz spacing. So if we compare these 2 solutions, in one case, we would have a 2 lambdas, so 2 times 200 gig in a slot, so 400 G per slot, giving ultra long haul distance. While in this case, we would have 1 terabit per slot, while giving long haul coverage of most relevant long haul networks. So it's a very economical way to build a metro regional long haul network. So let's talk about some actual results to really give you a look and feel of the capability of this 200 gig mode. So we at excessive tests with multiple, or also deployments with multiple operators. Here's an example of a China Telecom field trial where we used the 200G enhanced 16 QAM CFP, but we also used the 400 gig mini MSA line card and transmitted this 200 gig line rate over a distance higher than 1100 kilometers with more than sufficient margin on a 50 gigahertz spacing. And you see the link design on the left. You also see that this test was really with productized hardware, including a 100 gig Ethernet tester on the client side. So it was not just prototyping. This is a real product in the field. As you can also see from this little chart bottom in the middle, the constellation for enhanced 16 QAM is different from a classical 16 QAM. The dots have different size. So what's the reason behind it? I already mentioned it before. So we come to our last presentation slide for this webinar. As you see on the left side, we compared the 200 gig CFP enhanced 16 QAM mode with a classical 16 QAM, which you see left bottom. And on the enhanced 16 QAM, we use channel maze shaping, which is one of the main features. Also includes a probabilistic constellation shaping of the modulation, meaning the probability of each dot is different and makes the modulation looks more like a Gaussian signal, like noise. So compared to a classical 200 gig 16 QAM for the given distance of, in this case, was 1100 kilometers, the reach can, a number of spans can be more than doubled. So it's quite impressive. Of course, we know that 200G 16 QAM is not the only solution out there. So if we compare ourselves to off-the-shelf pluggable 200G 8 QAM mode, also in this case, you see that the transmission difference between the 200G 8 QAM and our 200G enhanced 16 QAM is quite significant. So we in fact truly offer a long-haul pluggable 200G solution with a density of 1 terabit per line card and OTN switch. On the right side, you see an example of an actual network upgrade was done in Europe, in the Netherlands, where an existing 40 gig system was upgraded with a 200 gig line side CFP without any changes to the chassis or the line system by itself. So we were able to crank up the capacity per fiber from 3.2 terabits to 10 terabits, so more than 3 times, decrease the cost of the interfaces by more than 70%, decrease the power consumption and the size of the equipment by around 50%, while maintaining the same long-haul transmission coverage. And again, there was no change to the existing line system. It's a seamless update over a live operating network. So with this being our last slide, it's been a pleasure.
Great. Thank you, everyone. We appreciate your being here. Thank you again for joining with us today. We'll see you next time.